Hello and welcome back to another video in the physics series on waves and light. Today we will be discussing the second refractive property known as Snell's law. Snell's law is a relationship between the angle of incidence and the angle of refraction between two different materials as light crosses the boundary between them. You will recall that the first refractive law was the law of the index of refraction, and it had the handy mnemonic, the greater the n, the greater the bend. And n values are found on the physics reference table in this chart. You should recall that the lowest value is 1 for air or a vacuum, saying that the speed of light in the material is judged against its speed of light in air or a vacuum. All numbers will be greater than 1 because it will show the ratios n equals c divided by v, which is equation W4. The ratio of the speed of light to the speed of light in that material is where the letter n is derived from. This is very important because when you have light traveling from one material, N1, into a second material, N2, there is an incident angle, theta 1, and then there is a refracted angle, which is based on the ratio of the indices of refraction, as well as the signs of the angles of incidence and refraction, respectively. Recall when we studied problem 50 with the water wave refraction, we were introduced to the concept of a wave bending as it crossed over a boundary. In particular, a water wave with a long wavelength and a fast speed hit this boundary and refracted at an angle bending towards the normal line, thereby slowing down the water and reducing the wavelength in order to make the ratio of speed to wavelength equal to the same frequency of generation of the wave. We then extended this concept for a light wave being emanated from this laser beam and then approaching the difference in two boundaries, N1 and N2, with most of the wave hitting the boundary and refracting off at an angle, with just a little bit of it reflecting off the surface. Now we're going to change the wave model into just a ray. So we know that the wave hits this boundary. It starts in this zone N1, index of refraction 1, and it goes into a different material. I've chosen air and water. So a ray of light from this laser beam will come out of the beam and will hit the water at the surface, making an angle between itself and the normal line. So this zone right here, this 60 degrees incident angle, is your theta 1, and it hits the surface and refracts and bends, getting closer to the normal because you've approached the boundary from a lower n value and crossed into a higher n value, low n to high n, slow down and bend towards the normal. This is the basis of the Snell refraction law. N1 sine theta 1 equals N2 sine theta 2. Let's take a look at the rule in summary. Refraction rule number 2 is Snell's law in words. Low N1 to high N2, slow down and bend towards the normal. And in mathematical concepts, N1 sine theta 1 equals N2 sine theta 2. We say this rule as a mnemonic: low to high, slow down, bend towards the normal. If you can remember that little mnemonic phrase, low to high, slow down, bend towards the normal, you will never forget that when a ray of light enters a new material from a lower n to a higher n, that material causes the ray of light to slow down and bend towards the material. Let's take a look at a sample problem with some mathematics. In the following model Snell's law problem, I have chosen to look at several factors such as angle of refraction, new speed, change in wavelength for a ray of light of frequency 5.09, 10 to the 14 hertz, traveling in air, which is incident at an angle of 40 degrees on an air crown glass interface as shown below. So here we have the black line in this diagram represents the surface, very similar to what you see over here. And one side is air and one side is crown glass. The ray of light is starting in the air, so N1 for air is 1, and then it goes into crown glass, and that's the second medium. N2 is 1.52. Let me show you where you find that on the reference table. When you want to find the index of refraction for a substance like crown glass, you can see that this chart is arranged in alphabetical order. So glass, comma, crown is 1.52. The first question asks, what is the angle of refraction for this light ray? So we know from the first refractive law that the greater the n, the greater the bend. 1.52 is greater than n equals 1. And we know from the second refractive law, low to high makes the light slow down and bend towards the normal. The ray of light would just continue in a straight line at its original angle of 40 degrees if this material was the same index as the first material. But since it is a larger number, low to high, slow down, bend towards the normal. So this red line represents the ray being refracted, and the theta 2 is clearly closer to the normal line than it was when it was on this side of the boundary, coming in at theta 1 of 40 degrees. So in order to compute the index of refraction, we have to use formula W5, and we have to substitute the given values. So let's see what those are. N1 sine theta 1 equals N2 sine theta 2. I put a green check mark over what was given. We know that we started in air, and 1 is therefore 1. We know that the incident angle was 40 degrees, so we have the sine of 40 degrees. We set that equal to N2, which is the crown glass of 1.52, which we looked up on the reference table. And we know that it has to be multiplied by the sine of the refracted angle, which is what we do not know. And that's what we're going to solve for. So in order to solve for this formula, we're going to have to use a little bit of trigonometry as well. So 1 sine 40 equals 1.52 sine of the unknown angle. We're going to take the sine of 40, which is 0.642, and divide it by the 1.52 to get sine theta 2 by itself. 0.642 divided by 1.52 is 0.423, which equals the sine of theta 2. To separate the sine from the theta, you have to use the arc sine function. Take the arc sine of both sides, and you get 25 degrees. And what arc sine means is the following. The angle whose sine ratio is 0.423, and that happens to be 25 degrees. This ray of light is incident upon this air crown glass surface at 40 degrees, but once it crosses the boundary, it now travels at 25 degrees to the normal. Let's take a look at another kind of question they can ask you in this problem. What is the new speed of this light ray inside the crown glass? Well, we do remember that Snell's law says low to high, slow down, bend towards the normal. So if it slows down from its original speed of 3 times 10 to the 8 meters per second, how much slower is it? We go to the reference table, we look at the ratio of N2 to N1 equals V1 to V2, which equals lambda 1 to lambda 2. And we see that this is formula W6 on the reference table. Now we don't need the lambdas at this moment, so we can just group, as I've done in green, the ratio of indices of refraction to the ratio of speeds. And we know that the V1 was the speed of light. We know that the V2 is the question mark unknown. Putting in the information that we have, N2 was 1.52, N1 was 1, C is 3 times 10 to the 8. We have a simple cross multiplication, and we see that the second speed, or the speed inside the crown glass, was equal to the speed of light divided by the index of refraction of crown glass, and it equals 1.97 times 10 to the 8th meters per second. That is much slower than 3 times 10 to the 8th meters per second. Question 3 asks, what is the wavelength of this light ray outside of the glass, meaning in the air, and what color is it? So what is the original wavelength? And we see that V equals F lambda, solve for lambda, and this original equation was equation W1. V equals F lambda, divide V by F, and you have the speed of light in air divided by that given frequency, which was 5.09 10 to the 14 hertz, and you have an original wavelength of 5.89 times 10 to the negative 7 meter. If you're not sure how to find the color of this wavelength, you look at the frequency, which was given as 5.09 times 10 to the 14 hertz. You go to the electromagnetic spectrum chart, and you find that 5.09 is between 5.03 and 5.20, and that's a shade of yellow light. Well, what is that change in the wavelength? Using V equals F lambda again, solving for lambda, we take the second speed and divide it by the original frequency, and we get 3.87 10 to the negative 7, which is a shorter wavelength than the original 5.89. So the wave has shortened its crest-to-crest wavelength. And finally, what is the angle of refraction for this light ray as this light ray exits the crown glass? So there's a very simple rule. Let's take a look at the reversibility of the Snell's law of refraction rule. The Snell's law of refraction rule says low to high, slow down, bend towards the normal. But what if you were going from high to low? Well, then you would reverse this. Instead of slowing down, you'd speed up. Instead of bending towards, you'd bend away. So the Snell's law rule is reversible. The exit angle will always be the same as the entrance angle when the light returns to the original substance. So here we have a light ray starting in air and going to crown glass. The angle of incidence is 40 degrees. The angle of refraction is 25 degrees. Now, when that same light goes from crown glass back out into air, the 25 degree refracted angle now becomes a 25 degree incident angle to the same kind of boundary, and it then refracts back out at its original angle of 40 degrees. Here's the proof for that. N1 sine theta 1 equals N2 sine theta 2. The N1 is now 1.52. The theta 1 is now 25. The N2 is 1, and the unknown theta 2 must be solved for, and you get the arc sine of 0.581, which gives you a 40 degree refracted angle bending away from the original normal. But this happens to match the original incident angle. We will now look at the reversibility of Snell's law. If a light ray travels from low to high, it must slow down and bend towards the normal. That's like if you were going from air into crown glass, as we did in our example. But when you go from the crown glass into the air, you're going from high to low. So instead of slowing down, you will speed up. Instead of bending towards, you will bend away. The refractive rule of Snell's law is reversible. You take this phrase and you do the opposite. Low to high becomes high to low. Slow down becomes speed up. Bend towards becomes bend away. Thank you very much for watching this video. It's a complicated concept. I hope you enjoyed it, and I look forward to seeing you in the next video.